Welcome to TennaTalk, a journey of discovery about all things antenna. TennaTalk is a production of the Antenna Whisperer, that's me, Rudy Wiedemann, K7RAW, and is generously supported and sponsored by the Las Vegas Radio Amateur Club. This is podcast number 6 on antenna modeling with EZNEC and SimSmith. So for today's agenda, we're going to talk about using EZNEC 2 Pro 2 Plus version 7.0, which is the latest version that you can download from EZNEC.com. And I highly recommend that you download that and make sure you have a copy of SimSmith and follow along. Try to reproduce what we're doing in real time. Stop the video if you need to, and you will learn very quickly. It'll be a tremendously powerful way to learn for you. We'll start by taking a look at where to find the existing models that come with SimSmith and where all of your models will be stored. We'll do a tour of some of the features. We'll then do some SimSmith analysis on a center-fed dipole, an off-center-fed dipole, an end-fed half-wave, and then for verticals we'll move to a whip with long guy wire type radials and a whip with short drooped elevated radials in the air. Finally, we'll talk about the power of the triad of EZNEC, SimSmith, and Nano VNA and how to use those in combination to really boost your antenna capabilities. So with that, let's have a blank screen and let's show you what EZNEC looks like when we bring it up. Okay, so this is our main EZNEC window. I can open up and I can show you. Let me bring up from the other screen. Let me bring up the dialog window here. And we're going to open up a 20-meter dipole right now that I've built previously. And the, let's see, dipole, 20-meter dipole at 20 feet up. That's it. Okay. Notice that right here, that title or title character, I use the same as the file name. The frequency is my general analysis frequency for analyzing things like my my launch angle profiles and such like this, because they change with frequency. Let's take a look at the antenna, view antenna here, and I have a dipole. Notice that you have control over all the different viewpoints. I can zoom into that and bring the feed point at the center of the view window, and with my ground plane or ground level down here, I can undo that. I can zoom in. I can pan left and right, in and out on any of the axes, and I can do a quick reset. So that's pretty handy, and you'll see there's other ways to use that. So how did I build this? I built this off of a single wire with a source or feed point at the center. So I click on the wires caret, and notice I'm going from minus 16.8 on the y-axis to plus 16.8 on the y-axis, both of which are at 20 feet. I'm going from N1 to N2 on this antenna, from N1, negative 16.8 feet, to positive 16.8 feet on the y-axis, that if it comes down, you see it's at the 0 point along the x-axis. It's in the YZ plane, if you will. Okay? So now let's take a look at sources. Sources is where I'm feeding it. So since I only have one element here in my antenna with 11 segments, which we'll get to here in a little bit, I'm feeding it at 50% from end 1. This is end 1, 50% from the negative end, so 50% from this end is right in the middle. And that's a center-fed dipole. So now I've created my wire, I've created my feed point. The rest of this, loads, transmission lines, transformers, and L networks, I'll leave to a more advanced session, but that allows you to do a lot of other cool things with your antenna. So now let's run an SWR. Okay, I use 3 to 30 megahertz with an 0.1 megahertz step. And now it's running that for me right here. And it takes a little while. Let's talk about segments. Segments let me break my antenna wires up in a way to place sources and loads and other such things with more resolution. And sometimes it'll complain that the segments are too long and I need more segments to shorten up the segments more for calculation purposes. So we're about done and it should pop up. Okay, it automatically brought up SimSmith. If I got SimSmith running, it automatically brings up SimSmith and puts last Z in here, which is the output file of EZNEC, and I say always reload. So let's go back to EZNEC and let's get SimSmith out of the way of my background and just look at EZNEC. And let's take a look at the SWR plot. So the SWR plot for this dipole, 14.1, it's resonant, 1.82, not too bad, not too shabby. Probably because it's only up at 20 feet, probably do a little bit better at higher elevation, but that's a good start. So now let's see what we can do when we drop it into SimSmith. Let's analyze this dipole, by the way, and we can see that on this curve, this is my 1.5, my 2.0, and my 3.0 SWR. 1.5 SWR from 13.91 to 14.45, more than the 20 meter band. I'm well below 1.5. So you can see I've got a very nice curve if I drop in an auto tuner into this and I analyze it at 14.2 and I auto tune at 14.2. I've got a very nice curve there. So let's see what else we can find with EZNEC about our dipole. And let's run a far field plot of the actual radiation pattern. So here's a three-dimensional far field plot of the radiation pattern at 20 meters for this 20 meter dipole. So this is a single band antenna, of course. And if I wanted to see the elevation pattern, then I could rerun that far field plot, and now I see a side view of that elevation plot, and I can see what the launch angle is and the dB gain at that max point and such. Not too bad. It's about what I would expect for a dipole. Notice here I've got this magenta line which tells me the current, where the currents are on my antenna, which is very, very handy. That's the heart of what EZNEC calculates, by the way, is the currents on the antenna. And see, it's maximum where the feed point is, which is what I would expect on a dipole antenna. So now let's take a look at a 40 meter off-center fed antenna and see what we can get. This is a classic. I believe I have one here in the file of available antennas. 20 meter off-center fed, that's a vertical. 20 meter off-center fed dipole, okay. So there's my 20 meter off-center fed dipole. I'm analyzing at 14.2 megahertz. I've got one wire with 20 segments from at 16 feet high, from minus 33 to plus 33, which is about what you'd expect for each leg on a 40 meter dipole. But notice it's off-center fed. I have a single element, so from end 1, I'm going 20% from end 1. This is end 1 here on the negative side, 20% of the total length in, and that's where I'm feeding it. Let's go ahead and actually get rid of this tuner and see what this says as its native output when we run an SWR curve on this guy. So let's go ahead and do that. Let's run an SWR from 3 to 30. I like to start from 3 to 30 and then maybe zoom in if I'm analyzing a much more specific range around a particular resonant part of the antenna, and be able to really zoom in and tweak very finely that way. All right, we're getting close. 5, 4, 3, 2, 1, bingo. Okay, so we can see what we would expect. Multiple resonant points. Here's at 7.1. Nice, 40 meters. 14.3, pretty darn close, right in there at 20 meters. 21.7, a little high for 15 meters. And 29.1, 29.2, a little high end for 10 meters. But not bad, not bad. Okay. So now let's do some analysis here. Let's see what the impedance is for 20 meters. Oh, no, let's just make it 15 meters. Okay. 21.7 is the frequency resonance and 126. All right. And that gives me an SWR of just below 3, of course. So 126 and minus 8 ohms, that means it's very close to resonance. How do I know? Well, let's take a look at the SimSmith chart and let's see what it's telling us. Aha! Notice that as I go across the frequency bands from 3 to 30, they spiral around all towards the 3 o'clock end of my Smith chart, which means that I'm well above 50 ohms. Remember, towards 3 o'clock is much higher than 50 ohms logarithmically. To the left of 50 ohms is much less than 50 ohms logarithmically until I get to 0 ohms or I get to infinity ohms. So as you may recall from an earlier podcast, I'm at the upper end. I have higher impedance, which is what I would expect if I'm off center fed. So right now, I'm analyzing at 14.2 megahertz. That's this bubble. So we want to bring this bubble, of course, to the center. And right now, I've got, with this bubble, I've got an impedance of, at this frequency of 111. So I need some kind of an unknown. And I can custom wind an unknown here. Let me drop this in. It's called an auto transformer. And let's drop this down towards 1. Okay. And now I'm close, 1.13. And with this, I would probably be able to operate this just fine for any rig out there with just an on. Okay. But if I wanted to be a little bit more persnickety, I could fine tune a little bit more. But before we do that, I want you to notice one thing. Look at the ratio here of the inductances, 5.6 to 2.266. All right, that's just about 2.5. Well, we said that the impedance was 111, which is almost very close to 2.5 times 50 ohms. So you can see that it's 111 at my analysis point at 14.2 megahertz. I'm inspecting it at 111 ohms. So that's not too bad, but I could actually tweak it a little bit more if I put a shunt capacitor. Nope, not a shunt capacitor. That would take me down. So let's throw that away. Let's go put a little bit of a inductance here. Yeah, that works. So now I can turn that down. I don't need much at all, just a little tiny bit of inductance. will bring me right into a sweet spot here of, let's see, I can, well, 1.013. That's pretty darn close to perfect. So if I really want to tweak it in, I could do that. Now, as you may recall, that was at 14.2 megahertz. Let's analyze this guy at 21.3 megahertz, and you'll see that it's going to be different. Okay, so here's my purple line. Here's my unknown is purple, so that's my purple line. So I have to change my ratio. Okay, so let me change that up a little bit. Let me change that capacitance, raise that up a little bit. And bingo, bango, I've got 1.002 SWR. Beautiful. And if I look on this curve, I can see that from 21 to 21.55, I'm less than 2.0, and from 21.7, boy, I'm right on the hairy edge, 21.7, 21.7. So 21 to 21.55, I'm less than 2 SWR. From here to here. That's not too bad. That's still not too bad. All done without an auto tuner. So if I want to operate, say, 2 or 3 different bands, I could analyze and figure out to build 3-tap unknown, a triple ratio unknown, with a appropriate inductor or capacitor that SimSmith tells you to use, and you're going to get really, really close. So that's a lot of fun. So that's an off-center fed dipole. Now let's take a look at an 80-meter end-fed half wave, shall we? Let me get rid of that, and let me open, and let me bring the file dialog box up here. And let's see what we can find for an 80-meter end-fed half wave at 50 feet. Cool. Okay, wire 2 segment length 2 long, L of 16.5 is what it is. Okay, conservative is 13, so I need more segments. So I'm just going to give it 11 segments, and that dialog box, complaint box, goes bye-bye. So now I'm going to change the feed point, and let me see what I've got. 1 source, 2 wires. Okay, wire 1 and wire 2. Why it has 2 wires, I'm not exactly sure. So let's go to minus 67 to plus 67 feet. And let's get rid of the second wire. We really don't need it. Okay, so now I typically feed it 5% from the theoretical end because what happens here is my counterpoise. I need a little bit of counterpoise on the end. So 5% from end E1 of minus 67 feet to plus 67 feet. And it's actually 2.6 based on the number of segments I've got. Let's boost the number of segments so we get better resolution, closer to what I expect. There we go. If I was asking for 5%, it calculates out to 4.9%, which is pretty much close to 5%. So now you can see I've got a little short counterpoise here, and the rest of it is this big, long 80-meter end-fed half wave. So let's go ahead and throw out these components and see what our native spectrum looks like when we run a SWR curve on this antenna. And let's do that right here, 3 to 30 megahertz, and off we go. So I would expect to see a number of resonant points on here, lots of them. And what's very interesting is if you have a long wire, you can add more of these half-wave lobes, standing waves, on your antenna. And the tuner, what a tuner does is basically adjust the electrical length of the antenna so that you get a nice even number of those little standing wave loops on your antenna. So here's a beautiful example of multiple resonant points from 29.2, 25.6, 21.8, 18.2, 14.6, 11, and 7.2. So I could probably afford to lengthen this just a little bit. So let's do that. Let's lengthen this guy just a little bit from minus 67 to minus 68 to positive 68 feet. And let's run another SWR. And like I said, tuner will actually change the electrical length to get it to look like there's a perfect matchup of an integral number of these half-wave standing wave loops on your antenna for that frequency. And that's the key. All right. So now this one's down here at 10.8. This one's at 7. This guy here is at 14.4. Pretty darn close. Okay. So let's minimize that. And this is the same curve you see in SimSmith. So here's the SimSmith analysis. And again, you can see that it's all bunched up and curled, wrapped around the 3 o'clock end of high impedance. So we need to go from here, and let's pick what band we want to tune up on. Let's tune up on, oh, this will be fun actually to see the bumps on here. Let's tune up on 10 meters. All right, and so let's analyze this at 28.4, and that'll be our analysis point. So we need to bring this guy, this bubble is at 28.4 on this wrapped up curly Q of curves as I go 3 to 30 megahertz. And I need to bring that over here to the center of my Smith chart, 50 ohms. So again, let's use an unknown, but I'm going to expect this unknown to have a much higher ratio, aren't I? So let me drop this down to close to 1, because it's just a little easier to compute when things are close. Then I can see the ratio here straight away. So now look at what's happening. My green dotted line down here is on my resistance circle, so I need to bring this up with an inductor, probably a series inductor, like that. Oh, look at that. Yeah. Bingo, bango, just like that, 1.009. All right. Now I want you to notice something. Remember, I start by pumping in 1 watt, and this is down to 99%, 99.353%. That's pretty darn efficient. That's a pretty efficient tuner, actually. So I can do that. But let's now look at what the antenna looks like. All right, let's take a look at the lobes. I promised I would show you the lobes. So to do that, the current lobes we saw before, let's run a far field plot. Okay, and I need to change the frequency from 80 meters to 28.4. And so it says segments are too long, you need to shorten the segments up. Okay, so for that frequency, I'll give it 101 segments, what the heck. Now I need to rerun the SWR curve for this, and then we'll do a far field plot, and we'll see what kind of current lobes we can get on this long end-fed half wave running at 10 meters. So we're getting close. 9, 8, 7, 6, 5, 4, 3, 2, 1. Bingo. Okay. Now, let's see here. Let's run the far field plot. Now look at this. Remember what I told you. Now you're going to get a number of these lobes. 1, 2, 3, 4, 5, 6, 7, 8 standing wave current lobes on this long end-fed antenna. And look at the complex pattern we're getting on 10 meters for this guy. Pretty hairy, pretty hairy. Let's take a look at a elevation plot. And yeah, we're getting several lobes, lots of energy at different angles. So end-fed, that's what you would expect with an end-fed half wave. Yeah, you can make it do it, but you got to trade off. Everything is a trade-off. So that was kind of fun. Now let's move on to a couple of verticals. And let's open up a vertical that I have in here that is a, let's see, it's a 20-meter vertical with a long guy wire radials. Okay. And so segment length is too long. All right. So let's change that to, let's change all of these to 11. And, oops, didn't want that there. And actually, let's save that for future reference. And edit, oh, it doesn't like something here. Yeah, okay, hold on. Let's get rid of this row. Accidentally generated a row in here. Okay, so now it should save. It should be nice and clean. And let's show you my dialog box up here. Let's save it as the same name. Yes, let's save it as the same name. Now let's take a look at our antenna. You can see that it's got these nice long legs. And notice that the guy wire style radial legs are about the same length as my radiator. So you can see it goes from 20 feet to 36 feet. That's 16 feet. That's the vertical radiator. And these go out from the center axis. They go out 12 feet, and they go down from 20 to 6 feet, which is about 14 feet. So away from the center 12 feet, down from the feed point by 14 feet. And so they droop down. Not quite 45 degrees, but close enough for government work. So you're going to find out something here pretty interesting when we mess with the length of the radiating element and mess with the vertical or the drooped radials. So let's go ahead and get rid of these so that we're back to seeing just the native start point of the antenna. Let's go back and run an SWR on this antenna from 3 to 30. And this will be interesting. So again, my analysis is a 14.2. That's right in the middle of 3 to 30. That's my center point. I like to start there because chances are most things are going to work around there. And let's see what we get. Let's see what we get for an SWR analysis, and let's see what we get for a radiation pattern. 8, 7, 6, 5, 4, 3, 2, 1. Bingo. Okay. So I'm resonant right there at 14.3. Not bad. Not bad at all. Let's take a look at the far field pattern. Oh, let's let's change the plot type to three-dimensional. And we get a flying saucer. Look at that. Pretty neat. But if I change the frequency to 15 meters and I don't have to worry about that, and I rerun the far field plot, look what happens now. I've got what almost looks like a hat. A woman's. This looks like the hat for the Queen of England, doesn't it? I think that's pretty cool. Anyway, notice again that you're getting all of the current in magenta. You can see here in 3 dimensions, which is pretty neat. And if I go to 10 meters and rerun, let's get rid of that. Come on, get rid of that. Rerun the far field plot. Okay, I get even higher brim or flatter brim, but a higher bulb top. So, and you can see imagine what it looks like from an azimuth elevation view. So I'm not going to run that. So that's kind of interesting. It's not bad. Works pretty well. You can see that for 20 meters, which is what it's designed for. 14.18 to 14.45, less than 1.5. So you might be able to tweak it, the vertical elements, a little bit to get that down a little bit. Probably get it resonant. Let's see, where is that? 14.45 to 14.18, still less than 1.5. You're pretty darn close. It's a naturally resonant at 20 meters. But if I want to make it resonant at something other than 20 meters, I could drop in a tuner right here and analyzing at 28.4, tuning at 28.4. And so, boom, I've got 10 meters there. And I've got my 10 meter curve here. And so 10 meters from 2782 to 2973, less than 1.5. Not bad. This will work very nicely. So this is as a naturally resonant antenna, they tend to give you a lot more tunability with an auto tuner, okay? Which is a pretty nice thing. So we could have retuned this with an on, sure, and you saw how to do that with the off-center fed and the end fed. But with the vertical, an auto tuner up at the antenna at the feed point is a sweet solution. So let's get rid of this tuner, and let's now do our final example, shall we? This is actually going to be our shortened drooped radials. And I'm going to actually show you one. This is pretty interesting what happens here. Very useful to know. So I'm going to take a vertical, 20 meter vertical with short drooped radials right there at 20 feet at the feed point. Okay, so let's zoom in on that a little bit. So that's what it looks like. I've got my vertical here. It is at 20 feet at the feed point at the base, up to 41 feet for a 21-foot length whip, much longer than 16 feet a minute ago. But here, I've only got very short radials. They're only 4 feet long, okay? You can actually use an 11-meter CB radial set from Wolcott Radio, and they have a kit for like $36. It's ridiculous, that you can use and create elevated radials, and it actually works pretty well. But notice, you're going to notice something. As you shorten the radials, you have to lengthen the center element, and it changes the performance because even at this feed point down here, you are it's a little bit like an off-center fed vertical dipole. and with 4 elements on this side of the dipole and 1 element on this side of the dipole. So if you had longer than resonant radials, then guess what? It would ask you for a shorter than natural resonant length vertical whip. So just realize that trade-off. So let's run an SWR and let's see what we get. So what would I expect? I'd expect, again, natural resonance. I might see another resonance or 2 dip. And the more off-center fed that vertical gets, the more challenging it is to tune it on other bands, as you'll see. And it changes the radiation pattern as well. So let's take a look. We're down here at 15.5. Wow, still too short. We need to lengthen it even more. So let's take it to 43 feet and let's rerun it. This is how fast. Can you imagine having to change your wire length on your antenna, go out there, climb up on the ladder, lengthen it, shorten it, and everything like that? Whereas you can do it here in a matter of seconds and instantly run the analysis. So it's really quite powerful. Notice that here it's using the last Z from EZNEC that automatically pops in here when you fire up EZNEC and then fire up SimSmith. It automatically loads that in there for you, and then sometimes it asks you if you want to always reload, and you should say yes. This is also where you would drag and drop your S1P files from your Nano VNA. But if you're using EZNEC, this automatically loads this name in here, file name last Z.txt, and that's the last impedance curve that you're seeing right here. Let's take a close look, and lo and behold, 14.5, pretty darn good. So let's take that. Let's see what the far field plot looks like. Oh, I got to change that from azimuth. Last time it was stuck on azimuth. Let's take a look at 3-dimensional plot. And again, we get some kind of a Queen of England hat at 14.2 megahertz. Okay, I can see my current, a lot of current on the vertical. Then I can have this distributed currents that add up, though, because each one of these currents have to totally add up on the 4 radials to the single current in the other direction, going up onto the vertical portion. And so now let's see here. I've got one nice curve, and oh look, it's trying to it's probably another dip out here above 30 megahertz. So let's do something fun here. Let's actually try tuning this at 28.4. So if I've already got my analysis at 28.4, it'll follow when I drop in a tuner, as you can see. So there's a tuner at 28.4. Let's take a look at the Smith chart, and boom, it gets us right in. And if we look at this, 28.3 to 28.64, all less than 1.5. Not bad. And we're still, with that same tuning, we're still pretty well tuned up. Nope, it shifted our 20 meters down frequency when it did that. So now that we're up here at 28 megahertz, let's do the same for EZNEC. And let's take a look at this top hat and remember what that looks like. And we're going to reanalyze this at 28.4 megahertz and run a far field plot like so. And lo and behold, it looks a lot different. It looks higher. Typically, if you're going at a frequency off resonance, and you can retune to it, but your radiation pattern will look significantly different. And you'll see it. Look at the standing waves that you get on here. So this is kind of interesting. So hopefully with that, you get a good feel for how to drive EZNEC and how to build models. What I like to do is, if I have an antenna in mind, then I'll build it quickly on EZNEC, run it on SimSmith, and go back and forth a few times until I get an antenna that looks pretty promising, and then I'll build it. And at that point, I have a pretty good idea I'm going to be in shooting range of having a working antenna. All I have to do is do a little physical tuning, and then I take a nano VNA scan, capture the S1P file, drag and drop it into SimSmith, and see what the actual antenna is actually doing. And then I can iterate by retweaking the either SimSmith downstream, like the unon or capacitor or inductor in front of the unon, or I can change the design a little bit in EZNEC, rerun the design, run it into SimSmith, and repeat the process. So hopefully you got a lot out of this. Hopefully now you're able to follow along and replicate what you see here. There's everything you see here you can build yourself and have a lot of fun doing it. I think it's good fun. So the next podcast is number 7, and we'll talk about diversity mode and SDR. Diversity mode is where you have a separate receive antenna and receiver in addition to your standard transceiver antenna and transceiver. And there's some real interesting features and some interesting tips and tricks to share with you on that. So with that, please click the like button, hit the bell icon, and click on subscribe to be notified for future videos. I got a lot more in the pipeline and love to share these with you. So until next time, 73, have a great day and enjoy all of the material. Have fun. Bye-bye.